Hi, this is Brock, Shin, and Zhang from Team YenYuan, and this is our final report on our NLP term project. First, we will introduce the goals of our system and then discuss the design and implementation aspects of each module. In designing the system, our task was twofold. Given a Wikipedia article and a number n, we generate n questions about the article that are each fluent and reasonable. Then, given an article and a set of questions about an article, we return answers that are each fluent, correct, and concise. In designing our question generation module, we made some preliminary observations. First, we know that after the initial sentence of a section, the subject of sentences is often a pronoun. To handle this, we perform co-reference resolution on the text and replace pronominal subjects with non-pronominal co-referential terms. Next, we observe that sentences in Wikipedia articles are generally syntactically complex. So to generate more fluent questions, we generate questions from simplified sentences extracted from sentences in the article. We used arcref to resolve pronouns so that we can generate good questions from sentences that have only pronouns in them. We only resolve for pronouns in subject position, however, because firstly, questions with a pronoun as subject are not good when decontextualized. Secondly, pronouns in other positions are often necessary for the fluency of the sentence. And third, because pronoun resolution is a hard problem, performing resolution on a subset of pronouns will reduce error. Because resolution is expensive, we opted to go section at a time, generating questions on resolved sentences in the section, and then moving to a new section if time permitted. To extract simplified sentences from a sentence, we first parse the sentence using a Stanford parser, and then use tregex and tsurgeon to extract sentences from non-restrictive appositives, relative clauses, and participle phrases that modify the subject-noun phrase. For each extracted sentence, we remove NP and VP modifiers and move sentence initial prepositional phrases to the sentence final position. We generate two types of questions. First, polar or yes-no questions are generated from a sentence by parsing that sentence using the Stanford parser and determining if it has an auxiliary verb using tregex. If it does, we use tsurgeon to remove negations, mark the auxiliary verb, and move it to sentence initial position. If there's no auxiliary verb, we find the correct do form based on the part of speech of the main verb of the sentence, insert it in sentence initial position, and fix the inflection of the main verb using the WordNet lematizer to get the bare form. The next type of question we generate is WH questions. To do this, we first supersense tag a sentence, parse it using the Stanford parser, clean it, and perform subject auxiliary inversion as we did for polar questions. Next, we add suitable WH words. If the sentence has a prepositional phrase that specifies a location or date, we remove it and add where or when to the front of the sentence, respectively. If the subject-noun phrase specifies a person, we remove it and add who to the front of the sentence. And if the subject is not a person or date, we remove it and add what. For question ranking, we use the Stanford parser to get the probability of each question's parse and rank them accordingly. We use this instead of a language model because we wanted to ensure that we got grammatical questions, given that we didn't build very sophisticated constraints on WH movement. Next, we just empirically saw that using this type of ranking got us better results than using n-gram rankings. Question answering. To answer a question, we first performed question processing, which was done by first determining the question type, either an entity or yes-no question, extracting content keywords from the question by part of speech, and then using the keyword stems, stemming the keywords with the poor stemmer, and then using the keyword stems to calculate TF, IDF values for each sentence in the article, and then ranking the sentences in the article by cosine similarity to the keywords. If a question is entity type, we determine what type of entity we're looking for using a map from WH terms to supersense tags, extract the top 6 ranked sentences by cosine similarity, and supersense tag each of these. Then we descend the ranking, and for each sentence we find all the entities that appear in both the question and answer and delete these. See if the sentence contains a unique entity of the right type. If it does, we return that entity. If multiple entities exist, we return the whole sentence as an answer. For yes-no question answering, we ran through a few ideas, each of which had significant problems. The first idea was to return yes if all keywords or stemmed forms of the keywords are represented in the sentence or stemmed form of the sentence. The problem here is that synonyms of keywords can be in the sentence, or hypernyms, and the answer could be yes. Antonyms could be in the sentence, and the answer could be no. Checking for these with WordNet we found to be too expensive and unreliable to justify. The next idea was to return yes, if and only if the cosine similarity was above a certain threshold, but we couldn't find any principled way to determine a threshold. Our next idea was to return yes if no negation terms are present in the sentence, but this is unreliable for various reasons. One final idea was to extract simplified sentences from the top-ranked sentence and return the smallest one with the same cosine similarity score as the larger sentence. The problem with this was that our simplification algorithm was just too expensive for the parameters of the assignment. So our compromise was just to return the top-ranked sentence, sacrificing concision for correctness. Thank you.